Okay, in this segment we're going to be looking at taking our SR latch and turning it into something called a clocked SR latch. And adding a clock to a latch basically allows it to only have its state changed when something is happening on the clock or at predefined points in time. Okay, so our clocked SR latch looks something like this. And this is the version that has the writability problem. You can also do the same thing with that we did to get rid of the writability problem with what we're about to talk about here. So that's another possibility with this particular structure. But we had cross-coupled connection here, and we had our, this is Q bar and Q, and we had our access devices. So this was S, and this was R. And basically anytime S was asserted, Q would be set high, and anytime R was asserted, Q bar would be set high and Q would be set low. In other words, the state of this latch would be set when S is asserted and reset when Q is asserted. And this is called an asynchronous SR latch, because these S and R signals can be asserted at any time. They don't have to be asserted only at certain times. There is no clock signal here that's orchestrating or sequencing things. And so to convert this into something that has a clock, what we can do is basically add some clock transistors in series with the access devices. Something like this. We have S here, and we put a clock transistor in series with it. So only when phi is high, S and R, here S and R affect Q and Q bar only when phi is high. So phi is the clock. So if phi is low, obviously the S and the R transistors are cut off, and asserting S or asserting R will not do anything to the state of the latch because the clock transistors are basically cutting them off. Okay, now this has the problem of basically weakening the access device, right? So when we have two transistors in series, as you'll see in the pre-lab for lab 6, if these two gates are both at 5 volts, it's almost like we have a transistor that is twice as long as either one of these, which has half of the strength ratio. And so by putting another transistor in series with our access device, we're basically exacerbating the writability problem. Okay, so these pull-up transistors here that these access devices are fighting against potentially have to be actually made weaker, where these transistors have to be made stronger to overcome these feedback devices. Okay, so that's one potential issue here. So adding this clock transistor in series with our access devices actually can exacerbate the writability problem. If we wanted to think about each half of this SR latch as a CMOS, a complementary CMOS gate, and go through the same exercise whereby we remove the writability problem, we could do that same thing, and what we would find we would have to add to eliminate the writability problem is a parallel connection of two transistors up here. And I will need to give myself a little bit more space, obviously. So I have two transistors in parallel. Here, where this is S, and this is R, and then this is the clock here, phi. So, if you go through that exercise where we observe here's the pull-down structure, or the pull-down network for each of the two gates that are participating in this, we have here two branches in parallel. One is the feedback that came from the feedback inverter, which is this transistor corresponding to this transistor in the pull-up network. And this in the pull-down network is in parallel with a branch that has two transistors in series. The corresponding piece of the pull-up network would be two transistors in series with this third one, and these are connected in parallel with each other. And so one is gated by S and one is gated by phi. So by adding these two extra transistors to each half of this circuit, we can eliminate the writability problem altogether in the same way that we talked about last time for the asynchronous SR latch that's analogous to this one, at the cost of, a couple of extra transistors. So this circuit is a clocked SR latch that is completely without any writability problem. Okay? So we don't often, in a context where we're building something like a register, work with SR latches. We typically will work with something called a D latch. And a D latch is one where S and R are strictly complementary to each other. And so we would take something like at in terms of the gate level implementation, or in terms of standard sort of two input logic gates, our clocked SR latch might look something like an AND gate going into so this would be R, Q, Q bar, get our cross coupling here. We have a second AND gate. And our clock signal is ANDed with our S and R signals. We've actually merged these two structures here together into a single monolithic gate with three inputs. The one that comes from the opposite side of the latch, the S input and the phi input. But to make a D latch, what we do is we basically have a D input and we invert D to generate the R input. And so a D latch looks like this. D stands for data in some contexts, or delay in other contexts. So in a digital signal processing context, we often will use these kind of circuits to implement a 1 clock cycle delay. But it's also the case that D could stand for data, because the value, the binary value that we're writing in to the latch is D. So D becomes Q when the clock signal is high in this case. Okay? So this type of latch is also called a level sensitive latch, because the D propagates to Q on the clock level. So D goes to Q when phi is high for this particular circuit. You could also imagine having D going to Q when phi is low. That would be another possibility. But level sensitive latches are very common. They're the simplest kind of latch structure that has a clock. But sometimes it's more convenient to work with what's called an edge-triggered D latch, or D flip-flop, where D propagates to Q only, let's say, on the rising edge or the falling edge of the clock signal. So not when the clock is high or when the clock is low, but D only propagates to Q on the next specified clock edge. Okay, so that's kind of the next level. This kind of D latch typically will be shown in circuit diagrams at a higher level with a symbol that looks like this, where this is the clock input here. So it's like a logic symbol, a typical logic symbol for a clocked D latch. So if we wanted to make an edge-triggered D flip-flop from clocked D latches, or transparent D latches, there are a couple of different approaches, and we're just going to talk about one. So the approach that we're going to talk about to making an edge-triggered D flip-flop is an arrangement which has a politically incorrect name, which harkens back to slavery. So we're not going to use that. So we're going to call this the leader-follower approach. So we have basically two clocked level-sensitive D latches, like so, and we are going to arrange them in a cascade. And we're going to feed the Q output of the first one into the D input of the second one. And we're going to put the clock signal in here to the first one. And then we're going to invert the clock signal into the second one. So this is D, this is Q, this is Q bar. And this is going to be the leader latch, and this is going to be the follower latch. You can probably guess what the politically incorrect name for these would be, but so here, when phi is high, the leader latch samples the input. And as long as phi is high, D will propagate to Q without any delay. So the value that the input has during the sampling phase will immediately appear here at this intermediate node. And we'll call this maybe Q prime or something. And D propagates to Q prime without delay. And this is the sampling phase. Of operation. When phi goes low, the leader latch stops sampling its input and holds the final value when phi went down. This is the holding phase. Okay? So when phi drops, the last value that D had appears here, and it's stable. The follower latch samples and follower latch samples Q prime, and Q prime goes to Q. So this particular arrangement would have the effect of D goes to Q when phi goes down. So this is a falling edge. Triggered D flip-flop. So if we wanted to make a rising edge triggered D flip-flop, which would have D propagate to Q on the rising edge of the clock, all we would need to do would be to flip the phase of the clock, which is sampling, or flip the phase of the clock in which the leader latch is sampling and when the follower latch is sampling. So to make a rising edge triggered flip-flop, all we would do is put the inverter here and take the inverter out here. So this would be a rising edge triggered D flip-flop. Okay, so that's all we're going to talk about with respect to flip-flops and latches. There's a whole other amount of stuff we could do on this. You'll get some of it in computer architecture if you take computer architecture, or you currently are taking computer architecture. You won't get it at the transistor level, probably, but at the gate level you'll probably go through like JK flip-flops and toggle flip-flops and all this kind of stuff. So we're just kind of maybe filling in some information that's complementary here that ties in with the transistor stuff we're doing. I want to go back and show you one example of a state holding gate that is actually quite a useful circuit. Okay, so we've talked about combinational gates, and we mentioned that state holding gates were gates that weren't driven high or low during some phases of operation. So an example of a state holding gate. Okay, this is called a Muller C element. Okay, and what we're going to do is we're going to have two transistors in the pull-up network and two transistors in the pull-down network, and both pairs of transistors are going to be in series. So we have two inputs A and B. And we're going to actually put this through an inverter, because typically the output has the same sense as the two inputs in a Muller C element, and this will be Y bar. And so we're going to want to go through the truth table of this gate and see kind of where its output is driven and where its output is state holding. Okay, so we have two inputs here, A and B, and we have Y. So we have four combinations. I guess I should say this thing has a symbol that's kind of funny. It has a circle with a C, and typically you have something like this. So it's not quite as common as some of the other ones, but you typically will see something like this: A, B, and C, or A, B, rather, I'm sorry, and Y. And so when A and B are both low, 0, so the four possible states of the input, 0, 0, 0, 1, 1, 0, 1, 1. So in the 0, 0 case, both of these transistors are off, but both of these transistors are on. So that means that this is up at VDD, or this is a 1, right? And so Y will be a 0. Let's go to the 1, 1 phase. Well, in the 1, 1 phase, so this is the 1, 1 phase, I'll have both of these transistors on and both of these transistors off. So the pull-up network is completely cut off, but the pull-down network is completely conducting, and so we have a nice solid connection to ground, so that Y bar is driven to 0 and Y goes to 1. Okay, but what happens in either of these two phases, where let's say A is 0 and B is 1? Well, if A is 0, then this transistor is off and this transistor is on. But the B transistors are in the same state as they were in the 1, 1 case. And so in the case of in the 1, 0 case, or rather the 0, 1 case here, the pull-up and the pull-down network are both cut off. And so this node is not driven at all. It's just floating. Well, this node is actually, or this is one of the two cases that where the gate is state holding. It just maintains its previous state. So y, whatever the previous state was, it maintains it. Now this particular implementation of the gate, so I guess I should say that if we flip this to the 1, 0 state, these transistors sort of flip their state from off to on, right? So this transistor is now off, this one is on, this one is off and on, but still both networks are cut off. So this is a dynamic, this type of implementation, the state here is actually held on whatever the parasitic node capacitance is. Right, there is some charge on this node. This node was charged up to VDD or charged down to ground the last time the pull-up or the pull-down network was actually connected to one of the power supply voltages. And so there will be some charge here, and there will be some input capacitance of this inverter here, and some drain to bulk capacitance of these two transistors, and some wiring capacitance here for the local interconnections. And that could amount to a few tens or hundreds of femtofarads at most, usually. And that charge sitting on that capacitance would be able to hold the state of the gate for at least some brief amount of time, but there are leakage currents that would subject that to bleeding away, or there may be some stray signals that come in from other lines that are kind of running past and they're capacitively coupled in here. And if I have a signal transition, which is called an aggressor signal, on this wire that's passing by, there will be a little divided down blip on this node. And so this is a dynamic, so-called dynamic node, or dynamic implementation of the C element. Dynamic in this sense is like the dynamic in dynamic RAM. You're basically storing the state, the digital state, as charge on a capacitor somewhere. And with dynamic RAM, you have to actually go back and refresh the charge. You have to read it periodically and rewrite its value before it bleeds away. And so we can fix this and make it static. And we'll talk about that in a minute. Okay. But what's this thing used for? Well, what happens is this type of gate is used to establish a consensus among the inputs. So the output transitions only after it's seen both transitions on the inputs in one direction. So let's suppose that A and B are both 0 and Y is 0. Well, then let's suppose at some point A goes to 1 and B has not come in yet. Well, it's going to maintain its previous state of 0 until B goes to 1, and then Y goes to 1. And then let's say B goes back to 0. Well, when B goes back to 0, it maintains its 1 value as long as A is still 1, but then when A goes back to 0 again, Y goes to 0. So it's only after both inputs agree and have made a transition will the output make its transition. So C here stands for consensus. Or at least you can think of it as standing for consensus. And this is used for completion detection in asynchronous digital circuit design. And those of you who are curious about that, you can talk to Ben, or not, you can talk to Ben when he gets back, but you can talk to John Say, who's teaching computer architecture. If you happen to be taking that class, he is an expert in asynchronous digital circuit design. And he can probably tell you much more about the use of C elements than I can. But this is a classic example of a state holding gate that's actually quite useful. Now, to make this not a dynamic element, what we will do very often is to introduce an inverter in feedback around this first inverter here. And this inverter here is called a staticizer. So it takes a dynamic implementation of a gate and it turns it into a static one. So here we've introduced a bistable element into the output of the gate that will have the ability to store a bit of information statically by the presence of this feedback here. We're encoding that in the stable states of this dynamical system. And so here we have a writability problem, and so this has to be made a weak inverter. So these devices in the inverter, here in the feedback inverter, need to be made long and skinny, and these devices in the C element have to be made short and fat in order to ensure that there is no writability problem. Or one other approach would be to take the same idea that we did where we had with the SR Latch that had the writability problem. We could introduce some additional transistors here in the feedback inverter to cut off the pull-up or the pull-down under the appropriate conditions when we want to actually change the state or need to change the state of the C element to make a fully static C element without the writability problem at the cost of introducing a few extra transistors. Okay? So this, I think, will conclude our little foray into transistor level digital logic design. We will talk more about this in Mad VLSI. If you're interested in this sort of topic, we'll probably delve a little bit more deeply into it in Mad VLSI, although it's not a full-on digital VLSI design class. So for those of you who are really digital circuit fans, sorry. I'm an analog guy at heart, and I do mixed signal stuff when I have to. But anyway, that's it for this segment. So we'll see you next time.